The most complex Chinese character still in use is the sinograph, and forgive me if there are any Chinese speakers here, Biang or Biang, I don't know, no idea, with 57 strokes, which refers to Biangbiang noodles, a type of noodles from China's Shaanxi province. I know that Shaanxi is there. So if you look at this, it's like, holy, you know, that's one of the things that I do find interesting about Chinese characters, is that they can be very, and as well Japanese kanji and so on and so forth, so they can be so complex. And this, of course, having 57 strokes would take a mammoth long time to write down, especially if you're doing calligraphy. Of course, I very, very much doubt that they would be, you would do this very often. You might do this once or twice. If you might do this to refer to the noodles on a menu, but then you probably wouldn't be writing this down if in a letter every time you want to send it. This does bring up an interesting point. I guess my point that I'm going to make about this is actually more to do with maths and coding than it is to do with cultural stuff about China, which unfortunately, ladies and gents, I do not know very much about Chinese culture. I have a friend who's Chinese and I make fun of her all the time, but that doesn't really count. Now, my understanding of this that's interesting from a maths perspective is this. When you look at the English language, we have like these letters, A, B, C, D, E, F, G, so on and so forth. And what I find interesting about this is that if you want to make a word, you have to combine letters together. And so, you can combine a word. You can make lots of different words which have, you can make lots of different words by combining one or two letters together. You can even have some words which are just one letter on their own. But of course, if you want to make a more complex word, the longer the word, usually the more complex the word is. And so therefore you have to add more and more and more letters in order to make it a more complex word. In some ways, however, and because we've only got 26 letters, that's the reason why we have an issue with, well, if you want to make a complex word, you're going to need a fair few letters and a fair few different combinations of those letters. However, if you're able to use a symbol, to represent, if you're able to use a symbol to represent some kind of word, and it doesn't require as many letters, then, if you're able to use a symbol to represent a word that doesn't require as many letters, then that symbol is going to mean that you can convey an idea without doing a lot of stuff. And so that could be an interesting approach, is that you don't need to use as many symbols, but you can still get your complex idea across. The difficulty with that, though, is that you will end up needing to have a lot of symbols. We can teach like a 2-year-old to memorize the alphabet, but to try to teach a 2-year-old to memorize every single word would be very, very difficult. So if you can imagine, like a 2-year-old only needs to learn 26 symbols, but in an English alphabet. But if you were trying to learn a more complex writing system that had pictures for words as well, they would have to learn a lot more. So there's a bit of a trade-off. With doing that, and that's sort of what we talk about when we talk about combinations in number systems and stuff like that. Like if you look at binary, yeah, sure, binary, you only need 2 symbols, but to do a complex word, a complex number like 13, you need to use a lot more of those symbols. Whereas we need to use just 2 symbols to make 13. But you could have a symbol for 13, but then you have to memorize 13 symbols. I'm going to stop rambling now. I apologize. I kind of went off my own little thing there. it interests me. That's why I'm sort of talking about it. It's just like I often find myself pondering. I'm like, would it be better to have more symbols, but then have to learn more, or have less symbols, but have to write more things down? I don't know. It's an odd thought. You know, maybe you might want to think of it, ponder it. But anyway, for those of you that have fallen asleep, let's get to the actual lesson. Lesson 57, frequency tables. We were able to construct a frequency table. Now, let's talk about this. So, firstly, what did we do last lesson? Last lesson we talked about, I'm not even going to go back to the other one. I'm just going to do this slide here. Last lesson we talked about data. We talked about how data is broken up into two major types, categorical and numerical data. Categorical, dealing with the quality of something. But when I say quality, I don't mean how good it is. I mean what things does that possess? What qualities do they possess? And so when we talk about qualities, we usually break that down into two things, nominal and ordinal. Nominal is dealing with names like hair colors, like eye colors, like country names, like you know. It can also deal with sizes. So if you've got like extra, if you've got like skinny, or you know, so on and so forth. Anything that's got a name to it is probably going to be nominal. Ordinal is also a categorical type of thing, but it's more good to do with ranking. So if I wanted to, like for example, you can't rank furry, scaly, you know, slimy. That would be a description. That would be this one here. But ranking, if you had small, medium, and large, that's going to be ranking. If you've got short, medium, large, that's going to be ordinal. Anything that's got an order. January, February, March, order. The next type is numerical data. So numerical data is data which has numbers in it. So 1, 2, 3, 4, etc. They can be broken up into two types. Discrete, which is an exact number. So it's like 3 pigeons, 4 children, so on and so forth. It can be measured as a count. So when I say numerical data, I'm usually meaning that you're counting. Continuous data is measured data. So that could be speed, mass, time, length, weight. If you measure something, if you measure voltage using a voltmeter, then that's continuous data. If you measure concentration, then that would be a grams per milliliter. That would also be a continuous measurement. So anything that is measured is considered to be continuous. That's why I tried to give you a clue when we did that question. I was like, oh, he measured the wind speed. That's trying to give you a bit of insight. But yeah, today we're going to be moving on to not really what is the type of data, but how do we record this data? How do we record data? We'll quickly talk about this briefly. Data is used a lot. I talked about this already last lesson, so I won't go into it. But for example, the data can be used for politics, planning, marketing, essentially anywhere data is used, you need to extract information from that data. When I say extract information, I usually mean extract meaning. It's not really, it doesn't make sense just to sort of say, oh, here is a bunch of numbers. We want to be able to extract meaning, and that's why we use statistics. Statistics helps us take a bunch of numbers and say, well, what does it mean? Once you have an understanding of what those numbers mean, you can move on to figuring out, well, how can we make an appropriate decision? So after that, we can talk about today's lesson, which is frequency tables. So we're going to discuss what a frequency table is. So I'd like you to jot this first phrase down, and then we're going to get to the rest of it. So a frequency table is a Frequency table takes a list of values and records how often certain values occur. This can often be done using a tally. If you don't know what a tally is when you take values and you write it down like this. The frequency, if you look at the picture on the right, it's an example of a frequency table. Here on the right, we've got a bunch of numbers between 1 and 5, and you can see there are two ones. Those two ones get recorded as a 2 in the frequency. There are 5 2s. Count them, 1, 2, 3, 4, 5. So that can be recorded as a 5 in this frequency table. You don't need to copy the frequency table down, as soon as you copy the main text. And so what we're able to do is we're able to record some information about the numbers that we've written down here. These would be, of course, for this example, these would be discrete values. So these could be maybe the number of, the number of children in a family, not sure. But yeah, like in families in the street or something like that, it could be the number of broken light bulbs in the person's house. You know, I don't know. But it's just a tally. It's just how many of those things occur. It's discrete, so you would count them. But this is a good sort of situation, but it doesn't sort of cover what happens if we have lots of values. And I'm going to explain how we deal with lots of values in a second. Okay, I'm going to change the slide unless someone says no, please, sir. I'm still copying this down. So this frequency table is great on the right. It just shows us how we can put these numbers into these spots. But it has two flaws with this particular one. This particular one would be great, but it doesn't explain how we would deal if we had lots of numbers, but it also doesn't explain more how we would deal with something like 2.5 or 3.9 or 16.2. It's been a bit loud. So we don't really know how we can use this. So let's now jump into this one here. This is our next idea. This is class intervals. Class intervals are ranges of equal size that data can be sorted into. For example, they can be sorted into ranges 1 to 10, or 11 to 20, or 21 to 30. These are class intervals. And if you grab a look here, the other advantage of a class interval that I haven't got written down here is that these are good for discrete and continuous data. And of course, you should be noticing here that we're not talking about categorical data here or ordinal data, but that's okay. We're just going to talk about these two here. And that makes sense. So for example, if I've got weight, so weight is a continuous data set, but if I've got 40 to 44 kilograms, that's pretty easy for me to know, oh, that's going to go, if I've got 42.5 kilos, that's going to go in that top one. If I've got 70.3332 kilos, it's going to go on the bottom one. And we can use those different values to get an idea. So class interval, it's just when we use the word class interval, and we're going to use the word class interval a fair bit, it just means the breakups. Now you can see on the right, by the way, these are broken up into groups of 5. 40 to 44 is a group of 5. 45 to 49 is a group of 5. 50 to 54, that's a group of 5. So you could break these up into 10, like the example I've gotten, 1 to 10, 11 to 20, so on and so forth. And so there are just different ways here. We can see that what they've done in this picture here is that they've recorded a tally, and then they've converted that tally to a frequency. And that's pretty easy. You just count the number of marks. 1, 2, 2, 4, 4, 5, 5. I should mention that when you, like, I know this is, for a lot of students, this is obvious, but, you know, I don't know what your backgrounds are, so I'm going to explain this anyway. In a tally, when you get up to 5, instead of doing 5 marks like this, your 5th mark actually becomes a line across. And so that makes it easy to count groups of 5. So when you get something like that, you can go, well, that's 5, 10, 12. So in this case, I can quickly see that that's 5 plus 3, there must be 8. 5, and straight away, without having to count each individual line. You never know where people are, what their backgrounds are. You guys may have never used tallies. You may have used tallies in a different culture which use different ways of sorting numbers. I have no idea. So that's that one there. Frequency tables, beautiful. Class intervals. The last sort of thing here is just to briefly talk about this word here, frequency. Now, frequency is a word that you guys are probably familiar with, but let's just get a definition down there too. Frequency is how often a value comes up or occurs. So it's, you know, if we can record that from a tally, how many times did this particular number, you know, show up in the data? You might not have frequency of a particular value. You might have the most common class interval. So you might have the interval of 40 to 45 might be the most popular interval, the highest frequency interval. But so it might not be a specific number, but yeah, you would still record frequencies. How often does a number fall into that interval? Relative frequency is a frequency as a fraction of the total values. And the last one here is percentage frequency, is a relative frequency in percentage form. Now we're going to explore all of these values and we're going to calculate them all on our own as well later on. But let's just go have a quick look here on the right just to see what those 3 terms mean. So we've got 2, 7, 20, 3, 4, 4. So, and this is like, for example, a degree, any number of the frequency. So this could be maybe the number of people with that degree that applied for a particular job. That, you know, that makes sense. So maybe it's like an MBA is like a master's of something. No, it's like not a bachelor's between them. I don't know what an MBA is, actually, to be completely honest with you. This is an American type of graph, but it's not really too important. But what I will talk about MBA is it's probably the most popular. 20 people have that out of the total 40. So if I go 20 divided by 40, that's going to give me half, or 0.5. And so that's how they get this relative frequency of 0.5. In comparison, 2 over 40 is actually 1 over 20, and that's going to become 0.05. Let's say you get this number here. But 0.5 is also equal to 50%. So then they say, well, the percentage is 50%. Half the people that applied for the job had an MBA. Only 5% of the people that applied for the job had just a high school certificate or something like that. Surprisingly, 10% had a PhD, which is very rare because PhDs are very difficult to get, but you know, whatever. But that's what these 3 different types of frequency are. Just to go on with, you would, frequency, relative frequency, and percentage, these show up not just, so this here, by the way, let's look at this for a second. This data, these are names. This is nominal data. Saying that, to be completely honest with you, I'm going to put in brackets. It is sort of ordinal. And I would, if I knew more about it, I might be able to say whether or not it is ordinal. The reason I'm saying it's sort of ordinal is that a bachelor's degree is better than a high school degree. I assume an MBA is better than a bachelor's, master's is better than an MBA, law is better than master's, and a PhD is better than law. So it could be an ordinal set as well. But I'm definitely going to say it's nominal. I'm not too certain about this one. But like, yeah, this is another way. The power here is frequency, relative frequency, percentage, these guys show up in frequency tables, in frequency table with ordinal data, with nominal data, with the frequency and relative frequency show up in tables with discrete data, and even with continuous data. Now, the point that I'm trying to get to, and this is going to be my last sort of idea that I wanted to talk to you guys about today, is how do you make a good frequency table? Like, what's the difference between a good one and a bad one? And there's one thing that will obviously many of you guys are probably thinking, oh, surely a frequency table is just you write down the class intervals or the categories, the different categories, and then you just write the frequency. And yeah, that's fine. That is actually correct. But there's one thing that I want to talk to you guys about specifically with continuous data and this new word that we've got for class intervals. I'm going to actually ask you guys in the chat, which one of these two do you think is better? The system on the left, which has class intervals of 0 to 5, 5 to 10, 10 to 15, or the one on the right that has class intervals of 0 upward, 5 upward, 10 to 15. I want you guys to write in chat, which one do you think is better, left or right? It's a 50-50 chance, so even if you have no idea, if you just guess, then you'll probably get it. I'm not going to move on until I've got 5 guesses in chat. Or if you want to guess out loud because you're confident. Left is better, left is better, left is better, left is better. I've got 4. No, I've got 5 already. Geez, that was quick. Can anyone tell me why left is better? Anyone tell me why left is better? Or we just know that left is better?
Because the right one doesn't properly represent.
Sorry, oops, sorry. Hold on. Let me just pump up the volume. I couldn't quite hear you just then. Can you say that again? Sorry.
Because the right one doesn't properly represent the data.
Because the right one doesn't properly represent the data. Beautiful. Okay. Beautiful. Now, let's look at why. Well, here's my question, right? If I had the number 5, the new piece of data came in, I had the number 5, where would it go in each of these scenarios? Well, in the one on the right, we would clearly say, well, it's the one on the right, this is from 0 up to 5, whereas this is 5 up to 10. So therefore, we would clearly put the 5 here, so it will turn into a 6. But for this one, where would the 5 go? Well, this is from 0 to 5, so I could put the 5 here. But I could also put the 5 here, because this is from 5 to 10. So this is 6. So this could be 6. And so the question, it becomes a bit murky. The question becomes, where would I put the number? And this is actually why, shock horror, ladies and gents, this one is actually the better table. The reason why this is the better table is because it very clearly says where different values should go. So what we would do is what these arrows mean, and usually we don't actually use arrows. Usually we would just use lines, like 5 line. What these lines mean is that these lines mean that these different intervals, this interval here from 0 goes from 0 all the way up to 4.9999, etc. And this goes from 5 all the way up to 9.99, etc. And so what that means is you can clearly know, as long as your number is less than 5, it will go in that top one. Whereas this one doesn't have the same clarity. It says, oh, you've got this number 5, and you could say the same thing about this number 10. Now, there are ways that you could change this class interval to be more like this one on the right. You could do this. You could go from 0 to less than 5. And what that would imply is, and then you could go from 5 to less than 10. And so that implies you go all the numbers from 0 to 5, but not including 5 to just below 5. And that's another way that you could use this. I've seen some people get away with this by going, well, you go from 0 to 4.99, and then you could go from 5 to 9.99. This is sort of okay. Because, yeah, sure it does. But the problem with that is, okay, so that means if I get a number, if let's just say I'm doing, somehow managed to get the number of grams in a particular bag to be 4.995 grams. It's like, well, which one does this go in? Does that go in this one? No, that's too high for that one. Does that one go in this one? No, it's too low, so it doesn't have a home. So yeah, there does become an issue with that. But in reality, are you going to get something like a number like that? Probably not. So this one is mostly okay. So if you guys see this one, you should probably be like, oh, okay, it's not that bad. It's not the end of the world. But even something like that. But again, if you get 4.95, where does it go? So that's how these work. So the moral of the story is, if you see numbers that look like this, then don't feel like that's wrong. That doesn't necessarily mean that it's wrong. It just means that you are looking for values between 0 and 5, but all the numbers between 0 and 5, including 4.9, including 4.8 and stuff. And then therefore, we know that if it is 5, it's bigger than this interval, so it goes into this interval. If it's bigger than 10, then it goes out of this interval into this one. And if it's bigger than or equal to 10, I guess is how you would think about it. So that's class intervals. And that's how you can create a class interval and what to put in it. What time have we got? Okay, we've got 10 minutes left. I'm going to do this one with you guys here. Now, I'm actually going to do something with you guys here, which is something that I wouldn't normally do. What I'm going to do is I'm going to do this question here. Now, because this is a very written question, I don't expect you guys to, I'm going to make this optional. If you guys want to copy this down, you can. If you guys want to work through this with me, then that's fine. You can do that too. I'm just going to do this one to show you guys how you can take a list of values and turn it into a frequency table. And yeah, you guys can follow along with me, but it's up to you guys. I'm just going to do this. Because I've got all the numbers in front of me, this is really easy for me to do, whereas it would be quite difficult for you guys to do. This frequency, and this should probably take us to the end of the lesson anyway. So this frequency table has numbers 3, 12, 6. What we're going to do, the highest number looks like it's 27. It might be a high number, but I can't see it. And what we've got here is we've got class intervals of 5. So this goes from 0 to 4.99999, etc. And this goes from 5, 10, 15, 20, 25 to 30. And see how I've got this symbol here, less than 30. So then that means that it's going all the way up to 30. But if I had 30, I wouldn't be able to put it into this table. I can only really put up to 29.999. So let's do this quickly. So how would I do this? So I would go, okay, 3, that's going to go in that first interval. I'm actually going to do a tally. 12, that's going to go into this interval because it's more than 10 but less than 15. 6, that's more than 5, so we put here. 21, that's in this interval. 23, that's also in that interval. 7, this interval here. 13, yep. 14, yep. 27, all the way at the bottom. 12, 7, I'm quite confused there. 15, oh, okay, 15 again. 15 is going to be in this bracket here because it's not 10, this is 10 to 15, but this is 15 upwards. 18, it's going to be in this one here. 17, also going to be in this one here. 11, this one here, put in a line because that's my 5th one. 10, again, this is 10 upwards, so the 10 is going to be in there. 2 up the top here, and then we've got 5. 5 is going to be in this one here because, again, this is 5 upwards, so that means it includes 5. Perfect. Now the frequencies are 2, 4, 6, 3, 2, 1, which makes our total frequency, by the way. 2 plus 4 makes 6, 6 plus 6 makes 12, 12 plus 3 makes 15, 15 plus 2 makes 17, yeah, plus 1 makes 18. I'm going to check that by counting these numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Perfect. Relative frequency. All right, what have I got? I've got 3 minutes left. Really quickly, let's do these relative frequencies. How do I do them? Well, I would go 2 over 18, which is, going to be equal to 1/9. That's okay. You could just leave that there, but we could just turn that into 2 divided by 9. I'm just going to round this to 2 decimal places. It's going to be 0.22. 0.22, which means there's going to be 22%. By the way, because that's 2, this is also 2, that's going to be 0.22. If that's 0.22, then 1 is going to be 0.11, which means that 3 is going to be 0.33. Let's do 4 divided by 18. If I made a mistake here, 2 divided by 18 is not. Ah, crap. Yeah, I knew I made a mistake. Whoopsies. Let's quickly get this done. Sorry, guys. I made a mistake here. This is actually 0.11, which is 11%, which means that this one is also 0.11, which is 11%, which means that 4 is double that. It's a 0.22, which is 22%. 6 divided by 18 looks like it's going to be a third, so 0.33, which is 33%. 3 is going to be ugly, but it's going to be 0.16 recurring, so 17%. And then the last one, 1 divided by 18, is going to be 0.055, which is going to be 6%. Then that gives us our relative frequencies. Each of those is just divided by 18, and then I put that into my calculator. Now, some of you guys may get quite nerdy, and you might then look at the percentages, and you might add those percentages up. And it is entirely possible that if you add those percentages up, they may not necessarily equal 100%. I think that this case they do. It looks like 7. Yeah, it looks like it's probably going to add up to 100%. But in some cases, you might get 101% or 99%. That's okay, because there will be some rounding going on in there. And so therefore, don't panic too much about that. But yeah, that's one of the reasons why we always save rounding to the end. So that's how I can create a frequency table. I first did a tally, and then used that to get the frequency. I use the frequencies to get the relative frequencies. So when 2 divided by 18, 4 divided by 18, 6 divided by 18, 3 divided by 18, 2 divided by 18, and 1 divided by 18. Then when I got them in decimals, just move the decimal point over to get percentages. Ladies and gents, next week what we're going to do is we're going to work on 2A and 2B. I might give you guys some maybe 15, 20 minutes to work on 2B at the start of next lesson, but 2A is a very, very simple exercise. I want people to finish 2A by the time we get back to class next Tuesday. So it's got something for you guys to work on. Otherwise, aside from that, we're running out of time, so I will see you guys next time. I will see you guys next Tuesday. Have a good weekend, and I will catch you guys later.